In this YouTube video, we'll be studying double-slit interference for waves of multiple frequencies. Usually it is done for only one frequency, having all of the components of all the different frequencies split up and treated separately. But if the different frequencies can be bonded strongly together with a constant phase, then they can interfere with each other and cause a unique interference pattern. Here is some data taken from a double-slit experiment for blue light with a single wavelength and frequency. Notice that all of the state variables are selected so as to produce bands that are 1 centimeter apart. The graphs of electric field and energy are shown, energy being proportional to the square of the electric field. This electric field bobs up and down periodically, and so does the energy. The energy distribution shows the placement of the bright bands. Here is a movie of how the electric field bobs up and down for blue light from double-slit interference. And here is the energy distribution bobbing up and down over time. Adding all of these over time gives us the energy distribution at each point on the screen, which is equal to the probability density function. Here is the data for infrared light. This sort of light has double the wavelength of the previous blue light. Its electric field and energy bands are spread out about twice as much as for blue light. This sort of light can be still faintly visible as red light. Here is the electric field for infrared light, bobbing up and down. Notice that it is slower than for blue, because it has a lower frequency. Here is the corresponding energy distribution for infrared light. If we combine these two types of light together so that they have a constant phase angle with each other, then they will produce a new entirely different interference pattern that isn't equal to the sum of the energies of the last two, so it is possible to create new sorts of interference patterns. This is how the electric field bobs up and down for blue and infrared bonded light. Notice that they do react with each other to make a new waveform. This is the energy distribution for this type of light. Notice that it produces a new and unique energy distribution, and not just the sum of these two energies added together. If the phase of these two types of light are phase shifted by about 0.07 radians, the longer wavelength of infrared being shifted, then this is what the electric fields and energy distributions will look like. This is how the electric field changes with time for this different sort of light. This is its corresponding energy distribution changing over time. Now these are the double-slit energy interference patterns for this mixed frequency light. The top shows these two frequencies of light being in constant phase and being bonded together, and so reacting with each other. The bottom graph shows the two types of light being independent of each other. Notice that the first graph has more prominent dark and light bands than the second. In this case, three types of light are bonded together, all of them having a phase angle of 0. Notice that this is a good way to manipulate the interference pattern. The third type of light is a higher frequency infrared light. In this case, where a third frequency is introduced, a new complicated pattern of changing electric field is produced. And this is its corresponding energy distribution function, which looks extremely complicated. Here I've contrasted the interference patterns of two types of mixed light. In the first, the different frequencies of light interfere with each other to produce strong light and dark bands, whereas the second produces bands that are not so pronounced. It may be possible to add different types of light together so as to create an energy distribution that is a single thin bulge in the center. and this could be an explanation of what a photon is, and how it can behave like both a particle and a wave together, since it is a wave packet and doesn't have a single frequency,